part two of the part two of our program. Up to now, we were talking about adversarial errors. Errors are introduced arbitrarily, adversarially by an adversary who knows how we're going to encode, how we're going to decode. In fact, would even work if the adversary gave the message to be sent to the sender of the message. So everything is adversarial, and still we were correcting errors. This was great, but it does leave us with some gaps, and I'll try to tell you about what they are. In particular, what we have not been able to do is deal with channels which can only send bits. So today we will switch and talk about channels which only send bits and try to tell you about that. You can interpolate between the two cases based on the ideas from today, but it will involve some new expressions and so on, which I will not get into today. So I'll start by introducing what's called the binary symmetric channel. And this will lead us very naturally to the notion of entropy, which is both very valuable in measuring what it is that we should be able to do, but also as a tool in designing the algorithms that will work. So and in particular today's, the next lecture's result will talk about these two aspects. I'll introduce some algorithmic issues related to the achievement of capacity and introduce the polar codes. We'll see how far along we get into that. The analysis of the polar codes is going to be the bulk of the last lecture on Friday. All right, so we already talked briefly about the binary symmetric channel. Today I'll flip, instead of using epsilon as the error parameter, I'll use P, just because it's built into so many of my talks that I might make the mistake anyway, even without intending to. But here's what the channel does. So there's inputs to a channel. You can put as input a 0 or a 1. If you send a 0, you get a 0 with probability 1 minus P. We usually think of P as being smaller than 1/2, often much smaller, but just think of it as smaller. So if you send a 0, you get a 0 with higher probability, but with probability P, it's going to be flipped to a 1. And this event is independent of all other events that we will be talking about. So other bits being flipped are all independent. If we chose a code randomly, it's independent of the choice of the code, etc., etc. Similarly, a 1 is transmitted as a 1 with probability 1 minus P and flipped with probability P, flipped to a 0. Okay. So very simple channel. And the question is, how do you correct errors in this? Now, Shannon, in his seminal paper, introduced this channel, and along with this, introduced this notion of capacity. He introduced a wide class of channels, but this one is good enough for all interesting discussions. It has errors, and it has algorithmic complexity when you're trying to recover from errors. So this is what we are aiming for today. Capacity is just defined as the maximum rate at which you can transmit over this channel, with the feature that when you encode your information and then you add the errors, in this case, the errors are going to be according to this binary symmetric channel. And maybe I'll introduce a new notation also today. You could also say that the errors are occurring according to the Bernoulli channel with parameter P and n copies of this drawn independently, where Bernoulli P is 1 with probability P and 0 with probability 1 minus P. Okay, so this is just the standard Bernoulli random variable. So you choose errors according to this Bernoulli random variable, n of them, and XOR them with the encoding of the message. And this is what the receiver receives. And now the receiver decodes it, and we want with high probability that this decoding should equal what the encoding was. The probability that you're not equal is, we want it to be negligible. As we send larger and larger and larger messages, this quantity should go to 0. We can achieve a lot better, but just looking at little of this will sort of keep one more thing sort of tame, and we don't have to worry about it. Okay, so this is just a definition. It says if there exists encoding and decoding, then the capacity is at least k over n. And so this is k over n. This is where it's being enforced. And if it doesn't exist, then the capacity is less. Now the question is, can we actually determine what the capacity of the binary symmetric channel is? And one of the main consequences of Shannon's main theorem here was the capacity of the channel equals 1 minus the binary entropy function with parameter p. What is the binary entropy function? Right now, I'll just define it as an expression and later explain why this expression arrives. Okay. So entropy of P is P times log of 1 over P plus 1 minus P log 1 over 1 minus P. Extreme cases, H of 0 equals 0, H of 1/2 equals 1. Okay. And this corresponds to the fact that if you have a bit, a Bernoulli bit with random, probability of being 0, of being 1 being 0, then it's really not got any uncertainty about it. So the entropy is 0. Entropy of 1/2 being 1 is saying that you have a completely uniform random bit, and that's a full bit of uncertainness. Now, when you see a theorem like this, it really has two parts. You want to prove that the rate is at least 1 minus entropy of P. It'll be obviously we're taking the limits of various quantities here, so it's sufficient to prove that the rate is at least 1 minus entropy of P minus delta for every positive delta. Okay, so for every delta, we'll pick n large enough and achieve this, and then this will tell us that the rate is that, at least that, but it only proves it's at least. And such a rate lower bound is a constructive result. You are giving a code which will, and an encoding scheme and a decoding scheme which will achieve this. But constructive doesn't mean polynomial time constructive. It just means, yeah, I mean, we're demonstrating the existence of an object. This one demonstrates the non-existence of an object, and it says that there is no code, no encoding decoding scheme which can achieve the features that we want, which will achieve rate which is greater than 1 minus entropy of P. It will never be 1 minus entropy of P plus delta for any delta that you choose. It will sufficiently large n, you'll start failing. Okay, so these are the two things that are associated with Shannon's theorem. So this, right now, we have introduced entropy as a quantity that is useful to measure capacity. Okay, so it's just, it's setting a target for us. It's not helping us analyze the target or get to the target. Later in the talk, we will get to that, and that because we want to get to that using themes which are information theoretic, we will talk a little bit more about entropy later in the talk. Okay, first let's talk about combinatorics. Why did this entropy appear in this expression? It goes back to some very simple notion. Okay, roughly when I transmit some sequence, let's say all zeros, and the binary channel is acting independently on every bit with probability p, what should you expect to see? You will expect to see roughly a string which has p fraction ones and 1 minus p fraction zeros, right? Because on each bit we are acting independently and I'm only sending zeros. How many possible messages, how many possible received vectors are there and what's their probabilities? So roughly you will see any one of points in a sphere of radius roughly p times n, where a sphere is defined as all the points, so sphere of radius r around a point x. So x is going to be in 0, 1 to the n. In both these cases, and r is integer. So the sphere of radius r around x is all the points which are at Hamming distance. In the case of the binary channel, Hamming distance is the same as pretty much any other distance. It differs in exactly r coordinates from y. Okay, and of course this is the size of the sphere is what we care about, and the size is not dependent on x. It depends on r but not on x. Depends also on n, the dimension in which we live. The ball is something which is where, you might say, oh, maybe I will get some messages which are closer, which won't have exactly p fraction errors, but less. Yeah, if you want to count that we call the ball. And the reason entropy shows up in all our things goes back to a simple way of counting the size of the ball or the sphere. If you count it, then you will get all these factorial expressions, n choose pn times blah, times blah, etc., etc. When you count all of those things, the expression you will get is basically 2 to the entropy of P times N. Okay, the size of the ball, the size of the sphere, they're all roughly the same, up to some small tiny factors like square root of N or something. And how large are they? They are roughly 2 to the entropy of P times N. So it grows exponentially with N, but it's not 2 to the N. 2 to the N is the total number of points, and 0, 1 to the N. It's only 2 to the entropy of P times N. And this is an upper bound and a lower bound up to some polynomial factors in N. So for the most of the talk, I will just be ignoring these parts, and because we, they will be definitely negligible quantities for us, and focus on this part. So the log of the size of the ball divided by N is converging to entropy of P. That's what we want to. That's why entropy of P becomes relevant for us. Okay, this is, and we'll even see it formally. Okay, so I'll very, very quickly skim over Shannon's proofs of how does he prove the capacity? How does he prove that there is a code and a decoding scheme which achieves at least 1 minus entropy of P minus delta? How does he prove that there is a scheme which achieves, no scheme achieves 1 minus entropy of P plus delta? Very, very quick sketches, and I definitely encourage you to look at these sketches as giving you ideas on how to carry out the proof yourselves, or look up further notes which will give more details. The capacity lower bound, Shannon was sort of very, very amazingly, early, and introduced this notion of the random encoding scheme. He picked a random error code completely, okay, for each message in 0, 1 to the k, its encoding is going to be a uniformly random string in 0, 1 to the n, and proved that it actually works very nicely when you decode with a very weak exponential time algorithm that I described here. Let me just take a look at the questions. For the ball, you assume P is less than 1/2. That's right. Yeah. So this all should have been for P less than 1/2. This entire discussion that we're talking about. Okay, good. Thanks. So what's the encoding scheme? It's very simple. It's just, it's not profound. It's just saying, okay, we know what to expect and we'll do that. And once again, throughout the discussion today, P will be less than half. Otherwise, we will get into all kinds of trouble, and I don't want to. So we are given a string Y. We want to know where did it come from? What was the X such that the encoding of X was transmitted? We want to pick sort of the most likely candidate, and we know that errors happen with probability less than 1/2. So we would like to, we would say, well, whichever has fewest errors, that's the most likely string. But we won't even go that refined and so on. We'll just ask the question. Let's look at the ball of radius roughly P plus delta times N around what was received. Okay. So what I transmitted, so this is 0, 1 to the N in my picture. What I transmitted might be this point. What you've received is here. So this is my Y, and that's encoding of X. What do? I draw a ball of radius P plus delta N around Y. If it has a unique code word, if there is a unique message M, such that encoding of message M lies in this set, then I output M. If not, I will just say, okay, look, errors. So there are two ways I might output error. There is nobody in the ball, or there are two code words in the ball. And I might have errors in more ways. It might be that what was sent was M, what is output is some M prime, and M prime is different from M because M prime is the only one in the ball and encoding of M is outside the ball. So there are three possible ways in which errors could happen, and we want to make sure that none of these happen with high probability. Okay. So, and what's the analysis? The analysis is really simple. Was there a question?
Sorry, do you mind explaining the third error again?
Yes, two kinds of error. The first two correspond to when we actually output error, when you have two things in the ball, or when you have 0 things in the ball. But you could also have one thing inside the ball, which is the wrong thing. M was transmitted, encoding of M was transmitted, but what you find inside the ball is encoding of M prime. Okay, great. So how can you have any of these errors? Well, first, the only way you can have the wrong thing being output is if the message M that was transmitted is very far from the Y that was received. Okay, more than P plus delta N far. What's the probability that that many errors happen? Well, this is standard tail inequalities, Chernoff bounds, and one can easily analyze this and say the number of errors happening in the actual transmission being more than P plus delta N is a very unlikely event, happens with probability exponentially small, which is little of 1 for sure. Okay, so this already rules out error number 3, because that would have said, well, the only way output the wrong thing is if M is not inside this ball, encoding of M is not inside this ball. It also rules out the other error, which was 0 things inside the ball, because now we know encoding of M is inside the ball. Only remaining possibility is there is some M prime, which also sits inside the ball now. Okay, so how do we rule that out? That's actually very easy to rule out, but you just have to draw the you have to separate the random variables and ones that you fix and ones that you consider random carefully. And the way we will do it is we'll say, let's fix what was received. Okay, encoding of M was transmitted, Y was received. Let's fix Y. Okay, now let's pick the encoding function. Okay, so really the way we design the architecture, the encoding is picked first, errors happen later. For the analysis, it's totally okay to flip them. So we'll transmit Y, now send encoding of, now we pick the encoding, and particular fix some message M prime, which is the wrong message. And what's the possibility that the encoding of M prime lies inside this ball? Well, encoding of M prime is a uniform point in the whole space. The probability it lies in this ball is the size of the ball divided by the size of the whole space. So that is 2 to the entropy of P plus some delta prime. Ignore this, 2 to the entropy of P times N, divide by 2 to the N. So you see the 1 minus entropy of P arising here, and that's exactly what goes into our final bound. So now we ask the question, what's the probability that there exists some other message which is transmitted? Well, there are 2 to the k such messages. You take the union bound over all of them, you add them up, and once again you get something which is little o of 1 here. Once again, this little o of 1 is exponentially small in n if our rate is sufficiently smaller than 1 minus entropy of P. Okay, so that's the entire proof of Shannon's achievement theorem. And of course, if neither of these happen, then we actually will output the transmitted message. The Shannon capacity upper bound is similar, but I will not do it. All I'll say is, well, it's about that long. If you just want to look at the essence of the idea, it's very, very simple. And now I want to turn to some algorithmic issues related to related to this thing. So Shannon has proved to us there exists an encoding function and a decoding function which will achieve this capacity of 1 minus entropy of P. Okay, but its running time is exponential. Okay, if I want to send k-bit messages, running times are at least exponential in k, maybe worse. So we don't like this. We want to improve on this. So the question is there an easy way to improve this? And actually there is a very, very, very simple, easy way. Okay, and that's what's suggestion 2. Okay, we have this huge message of length k that we want to transmit, but let's just break it down into sequences of length log k. Okay, and each one of these little blocks is of length log k. Use Shannon's theorem and encode each one of these using k codes of capacity 1 minus rate 1 minus entropy of P. Just independently encode each one and send it. That's it. Okay. What's the probability that you make an error on any one particular block, say this block, when we are trying to do the encoding? Well, the probability is exponentially small and log k. Make sure that that probability is actually smaller than even 1 in k square, or 1 in k, but 1 in k squared is good. Now, the probability that this block is recovered wrong is 1 in k squared. Probability there exists a block which is decoded wrong is at most 1 in k. Little o of 1, we are happy. Okay. Did that make sense? It's a very simple idea. It works. Okay. So when people say, oh, capacity has not been achieved, well, probably have some other things in mind because this is achieving capacity. So in those days, when we looked at this, we said, oh, but the error you can achieve this way is only 1 in polynomial in k. In general, the error will never be smaller than our runtime this way. Okay. Or error will never be smaller than 1 over the running time of the algorithm, just because that's the way that's the regime we are operating in. So if you want polynomial time algorithms, your error is going to be at most 1 in polynomial in k. So that seems sad. We really, having seen Shannon's theorem and knowing that you could get exponentially small error in k, now we're becoming greedy and we want to get to 1 in exponential in k. Can we get error which is exponentially small in k and with polynomial time algorithms, encoding and decoding? Okay. Might sound profound and hard, but it turns out this was also resolved. This is indeed where the context in which Forney discovered concatenation of codes. And this goes back to 1966. So and we talked about concatenation of codes. Here, the idea is the following. We have some message k, which is some k bits long. We first divide it into the usual chunks of size, let's say log k, and k over log k are chunks. Now you encode this whole thing, pretending it's a code over some large alphabet, log k bit long alphabet. So you can use a Reed-Solomon code, but this is a Reed-Solomon code of rate 1 minus delta. So it corrects very, very, very few errors. And that will give us some sequence. Let me use some different colors now. So the block lengths, if this is T, this is also T. Okay, so exactly the same T, but the number of blocks that we have is much more. Okay, if this was 5 things here, you might have 10, 5 over 1 minus delta. So this is, this went from k such blocks or k over log k blocks to that divided by 1 minus delta. Okay, so that's what we are doing. It's a code over a large alphabet. But now we have a binary channel, so we still have to send binary things. Now you apply Shannon to each one of these blocks independently. Okay. What does Shannon tell you? The probability that one of these blocks is going to be corrupted when you do the encoding and decoding is negligibly small. Little o of 1 is good enough, but actually it even gives you exponentially small in log k, which is the length of the block. So the probability that one of these blocks is going to be decoded wrong is very, very small, but it's not negligible. It's still 1 in poly k. You can now ask, what's the probability that delta over 2 fraction of the blocks got in error? Once again, Chernoff bounds tell you the probability that delta over 2 fraction of the blocks get in error is exponentially small in this length k. Okay, it depends on delta, but it really just does that. And so now what you have over here, since it has less than delta over 2 fraction of errors, we can go back to our algorithm for decoding from Reed-Solomon codes from yesterday and recover all this information. Okay, so a few errors over here is okay, because we've just put an overall code over here. What's the running time of everything? Well, encoding Reed-Solomon codes, decoding Reed-Solomon codes is polynomial time. And this part where we did encoding and decoding of log k bit long symbols, just like in the previous part here, it's going to take us polynomial in k time, exponential in log k, but that's polynomial in k. Okay. So with that idea in mind, we already have a great solution. You can actually, oops, what happened over here? Did I forget? Okay. So I wrote around some important stuff, so I'll try to remove all the writing so that we can now focus on the criticism of this thing. Now, how small can we make one of these blocks? Okay, if we want to get delta close to capacity. Well, if we want to distinguish between, say, errors with probability P and errors with probability P plus delta, P plus delta is more or less the same as entropy of P plus delta. So I will not distinguish between these quantities, some small number, right? If I want to distinguish between P fraction errors and P plus delta fraction errors, if it's P plus delta fraction errors, Shannon's theorem says I should not aim to correct errors. If it's P fraction errors, I want to be able to correct. But if I want to look at the difference between the two, I have to see the difference in each one of these blocks, because if I don't see that block, I don't get the Shannon's result, which says I will be able to decode this with high probability. In order to be able to see it in one of these blocks, this block must be of length at least 1 over delta square. Okay, 1 over delta square is the correct number, but just, it's clear that it should grow with delta. As you get closer and closer to capacity, the length of these blocks needs to get larger and larger and larger. And then the running time for the decoding, never mind the Reed-Solomon, etc., never mind n, just decoding one of these blocks, because we are using an exponential time algorithm, is going to take time 2 to the 1 over delta square. So let's look at its concrete implications. If you are working with a channel whose capacity is 90%, so very few errors happen, 90% of the bits should get through by our probabilistic analysis, and we want to use it at rate even 80%. We're saying, okay, 90% is the actual capacity, but I'm very happy to work at much lower rate. I'm giving up 10%, let's be fine. What will the running time of our algorithm be? It will be linear in n or polynomial in n with a constant multiplier in front, which is 2 to the 1 over 100, 2 to the 100, okay? So delta is 1 over 10, implies this part is a constant of 2 to the 100 times polynomial in n. It doesn't matter what the polynomial in n is, 2 to the 100 has already killed any hope of your being able to use this approach to get this close to capacity. So even though this is a very clean, beautiful idea in theory, in practice, it's failing because of this runtime challenge. Okay. So this is the challenge that remained open till basically this last decade. A code that was going to be able to deal with this was discovered only 12 years ago, and then the proof that it actually achieves, beats this bound was obtained about 7 years ago. And I'll try to tell you about those things as we go along. So let's write down what is the actual challenge. We are given P, the probability with which the channel is going to be flipping bits, and a delta saying this is how close to capacity we want to get. Our challenge in implementing this 4D scheme was that these codes needed to be of length 1 over delta, which is necessary. I mean, we don't expect to see codes of length log of 1 over delta or something much smaller, which will be able to distinguish between P and P plus delta, use the gap to capacity, okay? But the decoding time was also exponential in the length of the code. We want codes of the same length but we want the decoding to be polynomial time in the length of the codes. So that's the question that is being articulated here. I want a code whose rate is 1 minus entropy of P minus delta. Its length, so N, K, whatever you want to call it, they're both, by the way, within constant factors of each other if P is some fixed constant. Their length needs to be polynomial in 1 over delta. That's what we want. Okay. And we want to be able to decode these codes in time which is polynomial in their length, not exponential in their length. If I didn't want this restriction, Shannon achieved this. And if I didn't have this restriction, if I didn't have this restriction or that restriction, then the 4 knee codes that we just talked about achieved it. But we want both. We want this and we want this. If you want both, we don't know how to do it yet. And the goal of these remaining lectures is to tell you how to achieve these. Okay. Questions at this stage? So we are going to correct P fraction random errors. The length of the code has to be very short. We don't want long codes. We know that we can do it with very, very, very long codes. We want it to be happening with very short codes because in particular, we want running times which are polynomial in 1 over delta. And we are only willing to be delta far from capacity. Okay. So the brief history is that in 2008, Ari Khan came up with these brilliant families of codes called polar codes. And what I'll try to do today is to introduce you to the setup and some of the underlying machinery that leads to these codes. The formal definition of these codes and the analysis will come next in the next lecture. In 2013, a good 5 years later, even as soon as these codes were discovered, it was clear these were, immensely interesting, both from the theory and the practical point of view. In particular, Ari Khan had efficient algorithms, and that's the entire reason why we really, really loved these codes. But it wasn't formally proved that this actually solves this problem, but it does. And that was shown by in 2 independent works, Guruswamy and Shia, and Hassani, Alishahi, and Urbanke. And this is the result that we want to get to. I mean, if I don't have this result accompanying this, I'm not motivated to learn and present it. But when you combine the two together, the codes are beautiful and they achieve a mathematical theorem that I don't know how to prove with any other means. So that motivates me, and then I'm going to talk about it. The proof that I will be building on maybe next lecture, is from some paper that we've written, but that's just happens to be the direction I'm going in. Okay. So what are these codes? These codes are actually very, very, very information theoretic. They use notions from Shannon's original paper of entropy. And I think conditional entropy also appeared in the same paper, but I'm not totally sure. And they use tools about entropy. So if I give you a random variable, what can be the bounds on its entropy? If I do things like conditioning on random variables, what does it do to the entropy? How can I look at the entropy of a mass of random variables in terms of simpler quantities that's given by the chain rule? And what are some essential properties of entropy? So for instance, if I take a random variable over the set 0, 1, 2, and rename 0 as red and 1 as blue and 2 as green, well, the entropy hasn't changed even though the random variable has changed. So that kind of invertible maps leave entropy unchanged. This is kind of obvious and so on, but that's what you would expect from a definition of entropy, so on. So these are the tools from information theory. And in addition, there is some general probability stuff that we will need to be able to analyze these codes. And these are the tools, and based on these, the analysis works. So today we will start looking at some of the tools that we need here and talk about entropy and conditioning. Now, entropy we talked about earlier was the entropy of a number. From now on, entropy we'll really be thinking of as entropy of a random variable, where we should really translate from the previous one to the new definition by saying, oh, if this random variable was the Bernoulli random variable with parameter p, so 1 with probability p and 0 with probability 1 minus p, entropy of p would have been equal to entropy of that random variable. But entropy is defined for anything, and we will talk about entropy for variables taking values from a finite set, just because infinities confuse me. So x is some random variable. It takes values in some finite set omega. And let's say p sub I is the probability with which it takes some value I for any element I in omega. Okay. Then the entropy of this entire random variable, the random variable is really a distribution. You know, what are the PIs? They just completely specify the random variable, and or the underlying distribution. Really, the entropy should be associated with the distribution rather than with the random variable, but it's too late for me to get into that argument. Entropy of x is defined to be the summation of pi times log 1 over pi. Okay. So why is this quantity interesting? What does it mean? Informally, what entropy of a random variable x is supposed to represent is how many bits does it take to specify x. Okay, if I have some variable called x, you know, the distribution is known to me and you of x. So you know p1 to p omega, and I also know it. And now I've gotten an x sampled according to this distribution. I want to tell you what is x. How can I compress this information and send you something which will allow you to recover x? This is roughly what entropy is trying to capture, but it's not formally what it does, because if I have a single bit, I have to send you one bit of information, right? It doesn't matter how skewed the bit is. If the bit is going to be 1 with probability 1% and 0 with probability 99%, I still have to send you one bit. Entropy is trying to capture not how many bits do I need to send for this one choice, but what if I choose many copies of this random variable, x1, x2, x3, I have given n copies of x, all distributed according to this original same distribution, all Bernoulli P, let's say Bernoulli. Then if I want to send the entire sequence to you, then maybe I can do some compression of the global thing. Instead of sending you n bits, I look at this and say, oh, look, there's only 1% of these coordinates are ones and the remaining are zeros. I might be able to compress this whole thing and say, these are the coordinates where things are ones, and I send it to you, and you're able to expand it back and say, oh, these are the x1 to xn's. Okay. So entropy actually captures that quantity, the amortized cost of sending you a random variable where you and I know the distribution, and amortized in the sense when you choose many, many, many copies independently, I want to see on the average per copy, how much information did I have? How many bits did I have to send? So entropy can now be a fractional number. And this is exactly what it's supposed to be, even though there's a gap between what it means formally and what it is informally. We often look at this informal statement to say, does entropy satisfy, does some properties that you would expect out of this definition hold for entropy? And we will expect them to hold for entropy, and that's what guides us towards many of the things. Many tools in information theory relate to the fact that we have good intuition about this blue expression, and many of those intuitions hold for the green definition. Okay. So for instance, two very simple properties. If I have a random variable which takes values in the set omega, one way I can describe this elements, let's pretend omega is a power of 2, the size of omega is a power of 2, then I can just express all the elements of omega as binary strings of length log omega. To tell you what one of these variables is, I have to just tell you that log omega bit string. So I can communicate this x to you using log omega of bits, and that tells me that no matter what the distribution of x is, its entropy is at most log of omega. Formally, this also works out, and it's relatively easy to prove this. Okay. Now, another thing that I mentioned earlier, yeah, instead of, so this could have been omega and omega prime, it wouldn't make any difference. But let's say even if you have a function mapping omega to omega and it's invertible. So f is a one-to-one function from omega to itself, it's a permutation, then entropy of x is the same as the entropy of f of x. Okay, if I tell you what f of x is, you can compute x from it. And if you tell you what x is, you can compute f of x from it. So there's two inequalities here and both of them hold. Okay. And notice that throughout when we're thinking about entropy and saying, oh, should this property be true or not, we're thinking about this informal definition, but you actually prove it with the formal definition. And this formality can sometimes be a little extra work, but it can be done. Okay. So these two conditions hold. This is completely trivial. It just goes back and looks at this expression, whereas this one is actually takes a little bit more work. Excuse me. So entropy is one of the two tools. The other tool that we will be using is something very closely related to entropy. It's called conditional entropy. Morally, what it's trying to say is how many bits does it need to describe x, entropy of x given y? How many bits will it take to describe x if x is related to y and you already know y? Okay. I mean, x may or may not be related to y, but if it is related, well, and you already know y, then maybe I have to tell you less about to specify x. Okay. So for example, oh, I don't seem to have examples here. We could try the following example. If x is equal to y plus 1. Okay, so mod 7 and y is in 6. So y is some random variable which takes values in the set 0, 1, 0 to 6. X is y plus 1 mod 7. And the way we're choosing this is we choose a random y and then use x as y plus 1. But if you already know y, then I don't need to tell you anything in order for you to figure out what x is. You just subtract 1 and that you get x from that. So entropy is, for conditioning can sometimes reduce the entropy dramatically. But the very interesting statement about entropy is that conditioning does not increase entropy, but in expectation. So let's actually look at the definition of what is this entropy. What is the entropy of x condition on y? We are going to be looking at what happens when I pick y randomly. So x and y are jointly picked randomly. Now let's look at a particular choice of y, little y, condition on y, capital Y being little y, and let's see what does it take to describe x. But now we take the expectation over all the possible choices of y. For some choices of y, maybe this entropy is high. For some choices of y, maybe this entropy is low. The average, according to the distribution of y, is what we are measuring here. So this is one single quantity associated with two variables which are distributed jointly. Okay. So sometimes for entropy of x, condition on y can be larger than x. There can exist x and y says that this is true for a particular choice of little y. But on the average, you will always have a reduction or a non-increase. I'll abbreviate non-increase to reduces. It's a never increasing. Okay. So this is probably one of the most both very intuitive statements. It's also the essence of most of the, it's the most powerful tool in this area. At least to me, this is it's a very easily captured expression, which is more or less equivalent to Jensen's, I think. I mean, it's about that level of Jensen's inequality. It's about that expressive. And once you have this expression, you can get lots and lots of mileage out of it. Now, other nice tools associated with entropy are conditional entropy are the following. If I have two variables x and y, and I want to describe both to you, you have neither. One way I can describe it is I first describe x to you, that takes entropy of x bits. Then I describe y using the process which says, how can I describe y given x? And now it turns out that this is an equality. Okay, entropy of xy is exactly equal to entropy of x plus entropy of y given x. So not only is this one way to do it, this is the optimal way to do it. But once again, all of this is being said in this iterated n-fold repetition, etc., etc. I've only given you the informal interpretation of what entropy means. This is the formal definition. There is also a formal interpretation of this sequence, which involves n copies of x's and y's and so on. And when you do it for those n copies, this is an equality. Another useful fact is if two variables are independent, x and y really have nothing to do with each other. And you know why? Well, it doesn't help me in communicating x. So entropy of x given y is actually equal. But this is if and only if. Entropy of x given y equals entropy of x if and only if x and y are independent. I think we will only use the if direction. If they're independent, then the entropies are equal, but it holds in both directions. So these are very basic, very intuitive, very natural tools. If you haven't seen them, these are, it's a lovely, I think of the entropy as sort of one of the most powerful potential functions out there, and helps us analyze lots of interesting things. Today, it will build us a very, very neat, nifty code. I'll try to tell you a little bit about the code today, and then we will do a full thing from scratch next time. So what's the code? Before I get into coding, here's a very neat thing about error correcting codes, especially when you're working with a binary symmetric channel. Some of this idea will not work for other channels, and where it works and where it doesn't work. I mean, there's some intricacies. Let's not get into that. For binary symmetric channel, there's a very nice idea. If I know how to compress binary Boolean Bernoulli bits, then I know how to do encoding. The only catch is I have to have a linear compression scheme. So what do I mean by a linear compression scheme? I should build a matrix M. So we will be viewing from now on bits as elements of the field on two elements. So whenever I write any algebra, it's algebra mod 2, addition mod 2, multiplication mod 2. Okay. Anurag is asking a question. Can you explain how entropy of x given y can be greater than entropy of x for some values of y? Okay, sure. So let's take the following variable. If y equals 0, then x equals 0. If y equals 1, then x is uniform on 0, 1 to the n. Okay. And y is, and each one of these lines happens with probability 1/2. So y is 0 with probability 1/2 and 1 with probability 1/2. Okay. If you look at entropy of x, in this case, it will be roughly n over 2. Okay. Roughly, maybe I'm missing something. Entropy of x given y equals 1 is n. Okay. So this is an example where conditioning on some value of y, entropy of goes up, but on the average it doesn't. So if I condition on entropy of x given y equal to 0 is actually 0, and this averaging works out. Okay. So I mean, this is entropy of x in the first case is roughly n over 2. Maybe it's a little bit skewed. Great, thanks. Excellent question. Okay, so compression implies coding, and this is basic linear algebra, but we often forget it. But let's make this very explicit now. If you can find a linear way to compress, by linear way to compress, I mean if I have a lot of bits and I want to compress it, the way I will produce the compressed string is by multiplying with a matrix. Of course, by definition, what do I expect from compression? I should be able to invert the map. And when I'm inverting, which I call decoding, you won't expect a linear map. Linear maps will not work, and I will allow you arbitrary maps. But the forward direction should be multiplying by matrix. And most of the compressions that we, well, at least many natural compression schemes are linear. So this is not such a dramatic thing to look for, but the parameters we'll be seeking are going to be pretty strong. So I want to compress. So I have a long vector z. Z coordinates of z are Bernoulli, and each one is 1 with probability p and 0 with probability e. I want to multiply m by, z by some matrix m, and that will be my compressed version of z. Okay. If I can build linear compression schemes which compress Bernoulli p bits to their entropy, and how much is their entropy? There are n bits, each with entropy h of p, and we know that these are independent random variables, so the sum of their entropies is n times entropy of p. So this quantity should be roughly entropy m times entropy. The target should be like entropy of p times n. I'll allow a little bit of a slack. You should compress it to m bits, where m bits is a little bit larger, delta larger. The same delta that we've been working with all through the gap to capacity, the same one I'm allowing here. If you can do that and guarantee that when I actually start with Bernoulli random variables and I do a compression by the linear map, m times z is how I compress, and then I decompress by whatever decompression mechanism comes with this code, the probability I do not recover the original message is at most little of 1. I do want this decompression to be efficiently computable. That's the whole challenge. And if I can do this with n, which is Pauline 1 over delta, this would solve my Shannon capacity problem from earlier. So why does compression have anything to do with error correction? Well, it turns out this is sort of standard simple. This part is standard simple linear algebra. If I have a matrix M, so notice that M has M rows and N columns. I can design a matrix G with N rows and N minus M columns. So I'll call this K, which has the feature that M times G is identically 0. So when I multiply this with M, everything that I get is zeros. So this is the orthogonal space in some sense. If you view the rows of M as being vectors in some space, columns of G are coming from the orthogonal space, or maybe dual space or whatever. Okay. So I want this matrix and it exists, and you can always get K to be at least N minus M. Let's make sure it's N minus M and full rank. Encoding is going to be simply X goes to G times X. Okay, so if I have some sequence X and I want to encode it, I produce this encoding for the error correction. And this line tells you how to decode. I will not do the linear algebra, but I encourage you to look at the notes and see why does this work. Roughly, if I take whatever I've received and multiply it by M, then the X part vanishes, and all I'm left to do is to figure out what was the errors. The errors were Bernoulli, but what I'm seeing is actually M times the errors. And so, yeah, this is really what should happen, and that's what happens. And if you just put it all in notation, this is the single line of notation which tells you how to decode. If we have a decompression algorithm for a linear compressor, then we will be set. Okay. So the whole goal is not how to correct errors anymore. It is just compress information in a linear fashion. Okay. So Arikan's idea, brilliant one, in my opinion, is we will compress by doing something called entropy polarization. The extreme form of entropy polarization would be the following. I come up with some big n by n matrix, and I map Z to P times Z. Okay, and this will be an invertible matrix. Okay, so big n by n invertible matrix. So if I tell you Z, I can compute P times Z. If I tell you P times Z, I can compute Z. Arikan's idea is, let's set it up so that this matrix P can be divided into two parts. A top part, which we will call M, small top part, and the rest of it, which is R. And let's hope that when I look at so what is the entropy of Z equals the entropy of P times Z, right? Which is by definition the entropy of M times Z and R times Z. Okay, I mean, P times Z, what does it tell me? It tells me what is M times Z, and it tells me what is P times R times Z. Okay.
Sorry, why is the
Yeah.
entropy of Z equals to entropy of P times Z?
Invertible map. P is an invertible map. Okay. Does that make sense? Right.
Yeah, makes sense. Thanks.
Okay. So because it's an invertible map, these two are giving me the same information. I can apply, if you give me P times Z, I'll give you a multiply by P inverse, get Z. This is equal to that just syntactically. P times Z is these two. What we want to do is apply the chain rule here and say, maybe I can make entropy of MZ already all the entropy that I have, almost. And so there'll be very little entropy left. Operationally, actually, this makes sense. This is something I wish I'd thrown this into entropy. One of the neat things about conditional entropy, and we will use this, is that if, sorry, where am I? Yeah, I'm here. If I have some random variables, entropy of U condition on V is very tiny, some tau, then there exists an algorithm, a function, okay, f, that takes V and outputs U such that probability that f of V is not equal to U is at most tau. So conditional entropy has this operational meaning. If it's very small, it means that if I give you the second variable that you're conditioning on, then you can guess the first variable. In our setting, it will say that, oh, U and V, they're not saying that these are bits or whatever. U happens to be an n over 2 bit string, V is an n over 2 bit string, etc., etc. Well, whatever it is, if you give me the M times Z, there's very little conditional entropy left in R times Z, so I can guess R times Z. So given M times Z, I can guess R times Z, and given M and R times Z, I can go back and I have P times Z and I can recover Z. So this is going to be the process for decoding. So the whole goal is, can we somehow squeeze all the entropy? But unfortunately, we also need to squeeze it in such a form that this statement is not just true information theoretically, it's constructive. This algorithm needs to be efficient, and that's not guaranteed by information theory. For that, we will need to work. So what's Arikan's idea? It's amazing. He says, well, I'm not going to wait for 1 over delta bits to arrive before I start doing some polarization. Let me start as soon as the first 2 bits are given, I'll do some polarization. What can you do with 2 bits, which is somehow invertible? There's only one thing you can do actually, which is if I'm given 2 bits U and V, I can output U XOR V and V up to permutations of variables and names, etc. This is the only thing we can do, really, right? This is the only invertible map I know on 2 bits. And of course, nothing has changed. The entropy here is the same as the entropy there, but that's what we expect from invertible maps. But what has happened is this is actually a lot more random than either of these bits that we started with. It's not almost entropy 1 if these were something, but it's better than what we started with. And so if I look at V condition on U parity V, it's actually got less entropy than what we start with. So this has created a process which is slightly segregating. Okay, that tells me that my time is up. I'll just finish a couple of sentences and then I'll let you go. We're slightly doing some segregation. And in the next lecture, what we will see is how to repeat this process on many bits and not just do one step of segregation, but systematic polarization of the entire population of bits. And that will separate all our bits into very entropic bits and some almost zero entropy bits conditioned on the very entropic bits. And once I get we get, so, and in order to, we'll at least show you the idea, give you an idea of how the decoding algorithm works, and maybe some of the analysis which involves things like martingales, some general features of martingale polarization, as well as specific analysis of our martingale and its polarization. So these are the themes that we will do next lecture. So let me stop now. Thank you.
Thank you very much. Maybe somebody have some questions.
I have a philosophical and stupid maybe question. So there are, of course, if there is a code which works in the adversarial setting, it will also work up to some extent in random setting just because of the number of errors. But what happens if we take some good practical code for adversarial setting and try to use it in the Shannon mode? Do we normally get something which is better than this guaranteed behavior, and maybe even better up to the bound, or there's different things, and you cannot use code which are good there now?
Okay, that's a wonderful question, Sasha. So what happens actually is mostly we don't know. Okay, that's the first bit of answer to your question. Can we use a known code which works well against adversarial errors to do something? Actually, you don't know. But in retrospect, after Arikan's polar codes came along and people looked at this matrix that he was using to polarize, and you looked at what were we doing with it, people realized, oh, this is actually the same matrix that we would use for a Reed-Muller code, or maybe slight variations of it. And then they went back and looked, and it took them this process of analysis to realize, oh, actually, Reed-Muller codes would have actually achieved capacity, but we only know how to prove that in the case of the binary erasure channel. For the binary error channel, we do not, the symmetric channel that we've described so far, we actually don't know of any natural code which achieves this. It is the other thing that I would feel is, I only know what's known in theory. People like Arikan and others have vast experience playing with actual codes and seeing how they work in practice. And the kinds of statements that we are asking can be tested and validated empirically. And my sense would be that they have figured out that this doesn't really work for most of the other codes that we have tried.
Thanks.
Sure thing. Other questions? All right. If not, let me stop now. I'll stop my screen share.